got sound working, and apparently we have an excellent connection.
There's 0 views.
Pardon? Well, yes. It's not like I have people rushing. It was weird when I would turn it on and all of a sudden it would go 1, and I'm like, who's watching this? Why is there no picture? There should be a little bit of a picture.
I bet one day some person will find, like in 1,000 years, some person will find your live streams on YouTube and make a documentary about the mysterious Mr. Neufeld.
No, I deny that. Oh, it seems to be streaming, so I'm just going to believe it.
Why do you deny that?
Deny what?
The fact that in 1,000 years people might watch your streams and make a docu-series about you.
You know how people say that once it's on the internet, it's forever?
Yes.
That's a lie.
Nothing's forever.
Nothing's forever, and stuff disappears on the internet all the time. And if it's on the internet, it has no physical backup, it's most likely gone in a very short amount of time. It's just the stuff you don't want that's forever. All the good stuff is gone. Okay. We left off here. So, notebooks out. There's nothing that was particularly bad about these models. You did them on the board. They were correct. You like to draw big circles, and it's not a better Bohr model, but it's a more efficient Bohr model. And the more efficient Bohr model is if I asked you to draw like 20 Bohr models, this would take you a long time. It would also take me a long time to mark because it's difficult to see what's there. So many times you're allowed to do something like this. 3 protons, 2 electrons, 1 electron, and you're done. You know that's a nucleus because it has a proton in it. If you really needed to, you could put in the neutrons if you were asked for it. And then you have your electronic structure. If you want to be really condensed, you can also do that. You have the electronic structure, the number of electrons in each shell. Question?
No.
Okay. Do you have your notes?
Yeah.
Okay. You have the electron structure, you have the number of protons, you're good to go. So when I'm asking you, unless you need this particular version for some reason, there was also one model last day that drew it like this, where they paired those ones up, and then they went on to the next one. Who did that? Excellent. Who's your teacher in Meta? Did you go to Meta?
Yes, Miss Stevens, but she didn't do it like that. Miss Chung did.
Ah,
Copy
I am
Miss
learning
Chung.
a pattern. Miss Chung teaches it properly. If you learned it the other way, that's fine. Lots of people do for grade 9. But the first energy level actually fills 2, and they pair up. So this will come in handy later if we're when we're doing Lewis dot diagrams. And they also pair up if you add more. So if, for example, you kept adding electrons and you're adding 8, you would then start adding them. You can go clockwise. So 1, 2, 3, and you'd space them out evenly. But as soon as you filled up the 4 points of the compass, you would start pairing them. Because there's only a certain amount of spots for the electrons. There's only 4 spots in total. And we want to, and once the 4 spots each have 1 electron, they then start pairing up. Did I use the bathroom analogy last day? Electrons are like when you go into a washroom, there's all these stalls, all of them are free, so obviously you go to the last one that's the furthest away, you're hoping it'll be the cleanest, and then someone else comes in. Do they take the stall right next to you? No, that would be insane. They're like, we want to be really far away from you. They leave stalls in between, and then someone else comes in, they take another stall that's far away, but eventually every other stall is full, and then people have to start pairing up. Same with electrons. There's only 4 stalls until they have to start pairing up again because there's only 8 total. In the first one, there's only 1 spot total because it only fits 2 electrons. What's the pattern for electrons? How many fit in the first shell? 2. How many fit in the second shell? 8. How many fit in the third shell?
Also 8.
I thought did someone say something? How many fit after that? Not 16. Not 32. take out your periodic table.
Yay.
We will see a fundamental law of the universe just built into its structure,
I wonder if I have periodic table. It's just had a bills.
which is kind of weird that you can do that.
Which periodic table?
You found the periodic table?
I found 3 periodic tables. I think you're in the wrong book.
You just need this one, or the clear one, the non-colorful one, doesn't matter which. How many elements are in the first row? No, the first row. 2. If you said 3, it's because they repeat hydrogen. The reason they repeat hydrogen is because it could be +1 like these, but it also could be -1 like these. So this particular periodic table prints it twice, just to confuse you. So there's 2. How many are in the second row? 8. How many are in the third row?
Also, 8.
Also 8. And then how many are in the fourth row? Count along. 18. There's 2, and then here there's 10, and then here there's 6. So 2, 10, 6, 18, and so 18 fits into the fourth energy level. The periodic table by row, you can just count the number along and you'll get the right number. If you want to know how much it would be in here, this actually continues down here. So it'd be 1, 2, 3, 4, 5, 6, and you go all the way along. You just count the whole thing and you get the number. And this was made before they even knew what an electron was. Mendeleev in Russia, when he first put this together, had just basically all the elements and their properties written on cards, like a stack of playing cards. And he would just put them down and try and arrange them like families. And then he managed to create this structure, the periodic table that reflects the underlying atomic structure, because the atomic structure affects its properties. Does anybody, speaking of which, know why it's called the periodic table? Yes.
Because the range of periods.
Yes. But that begs the question, why are they called periods? Louder?
Share the same properties.
What share the same properties?
The columns, not the periods.
The columns, not the periods, yeah. So what it means is if you go along,
The period's the
you have, lithium, +1 metal, reacts explosively with water, and then just to simplify, we got a +2 metal, +3, ±4, -3, -2, -1 noble gas. And then you have sodium, +1 metal, reacts explosively in water. The properties repeat periodically. Down to the root meaning of the word period, which just means something that repeats on a cycle. And the periodic table repeats on a cycle. And since it repeats on a cycle, you've got 2, 8, 8, 18. Also, you will see printed, hopefully in your textbook, and any other textbook, they will not show you 2, 8, 18. They will just say 2, 8, 18. Does anybody know why? There's a little bit of a lie that's built into what we're teaching you about the Bohr model. Why don't I just use an extra one up here? I'm going over there, but then the people over there can't see very well the way I've arranged the classroom. So we got 2, 8, 8, 18. And I've just told you textbooks will say 2, 8, 18. How that works is that that's not really 8. We do have a 2, but that's a 2, 6. So that 2 is repeated in another energy level. This is the first energy level. This is the second energy level as you go out in the ring. As you go to the next ring, this is also a 2, 6. But then there's a 10. And how that works is if I was to just represent the first energy level, you have 1 electron and then another electron. And then if I go the second ring, so we started here, that's the nucleus. We have our 2 electrons. Drawn backwards, I go to the second one, which is here. Draw another one, but then I draw the next one. So it goes 1, 2, 3, 4, 5, 6, 7, 8. So there's our 8. They fit in. They're slightly different levels, but they both fit into the second level. So that's here. So that's our 8. Then we have the third level. And the third level has that first one as well. And then it has that one. And then it has this one. So we go 1, 2, 3, 4, 5, 6, 7, 8. And then how many electrons would fit into this based on that pattern? No, you've already asked lots. Hands, yes? 10, because there's 5 there. And we're at this one where it's also 8. And why don't we consider that? Why do we stop at 8 in the Bohr model? And the reason is, I'm going to draw it in a different color. At the fourth level, so if I just draw another circle, we went 4, it would be, 4 would be there, and then there, 2, 3. So you fill up this, and then you fill up this, and then where are you going to fill up next?
The 10.
Yeah. So you go here, here, and then you go there, 2, 3, 4, 5, 6, 7, 8, 9, 10. So even though all of these, whoops, go away, I drew that wrong. No, stop it. Go away. There we go. So when we're filling this, different color, is all the third energy level, but it fills up in this order on the fourth. It fills up that, and that, and then that. So it is until here that you see 18. The Bohr model wasn't able to explain that. This is actually a quantum model of energy levels. And it explains more properties. You'll see this next year. And this is where I get to say, you're actually forbidden to know that because that's quantum chemistry. And so we're going to stick with the 288 model. But you should be aware, there's a deeper understanding there. It also affects the shape of the electrons. When we did that, that's where that comes in. And now we're going to ignore it and just pretend 288 is true. Fill out the table. With your knowledge from grade 9, what is the symbol charge mass in AMUs and location of all the subatomic particles?
For electron, we write just negligible.
Pardon?
For electron, do you write negligible?
You write whatever you think the correct answer is.
Nice.
And then I am going to ask someone at random to fill out a column. So I have a new app. So I go to the app, I click on Science 10E, and then you all show there as little monsters or eggs, because this was originally made for kindergarten students. And then I press the word, oh, hold it, I haven't done attendance. While you're doing that, I'll do attendance first. Aiden?
Yes.
Arnie? Arnie?
Yeah.
Arnie?
Yeah.
Oh, there you go. Bowen?
Hello.
Graham? Chef. Quick. Grayson?
Here.
Jamie?
Yes.
Layla?
Yeah.
Liam?
Here.
Mary? Marie?
Me?
Yep.
Oh, Mari.
Mari? I should go in and fix that later. Matthew?
Yeah.
Miyabi? Nick?
Yep.
Noah?
Here.
Rachel?
Yeah.
Rose?
Here.
Violet? Violet Corley?
Just over here.
Not here. And Yuma? Excellent. Well, here's some one. Knows who's away, and then I hit random, and then it says Arnie. Where's Arnie?
Yeah.
Excellent. So you're next. I'm going to ask you in a moment. You're going to ask you to just name. Since you're first, you get to pick which column you fill up. So we won't do it just yet. I'll give everybody 30 seconds. But you're also winning because you have 1 point, and everybody else has 0.
Nice.
Yeah.
Okay.
The reason I do this, just so you're aware, number one, I've told you where to sit in the classroom if you want an A. I did that did I do that the first day?
No.
Okay. If you don't know your teacher, this goes for any classroom, particularly useful in university. If you want an A, where do you sit? Which side? In the middle, no.
Left.
Who's left?
Teachers.
Oh, your left would work. Yeah, my right. Why?
Because people look to their right more.
More people are right-handed than left-handed, so that's my bias. That is a natural bias that every right-handed person has. So on average, if I'm just going by my instinct, I'll tend to focus on these students. They'll get more feedback. They'll get more critical feedback. They'll get noticed more. And then that would mean that the worst spot to sit would be back there. I'll never notice you. Also, I'm just noticing we're a very segregated classroom. You could almost run a line right here. I'm not going to say on what basis. Maybe I should disrupt that. Anyway, teachers have all sorts of biases. Maybe I'm going to pick on you because you happen to be wearing a red shirt and I noticed that more. Or maybe I'm colorblind and I only pick on the people who have white shirts because I know what color that is. There could be, maybe I only like people with long hair. Boom. Those people get more attention. If I use the app, then it doesn't matter my bias. I'm going to call on you every once in a while. And say you go to like Hawaii for 2 weeks and your parents rip you out of school and you're so sad because you're in Hawaii and you'd rather be here doing chemistry, but you miss all the questions. I'll know when you come back because you won't have as many points. And then I can ask you a ton of questions until you're caught up. Moha. Moha. Yes. What do you have?
I have a question about this.
Yeah.
I actually moved up a year, so I didn't do this last year.
Oh, well then you're about to learn. You're allowed to consult with anybody around you. So you can move your desk around if you'd like, or move your seat around and just sort of peer over, and then just keep up the best you can. And what I can tell you is that everything you learn in grade 9, we repeat in grade 10. And how the BC curriculum works is that you introduce it in grade 8. You repeat everything from grade 8 and grade 9 and add a little bit more. You repeat everything from grade 9 in grade 10 and you add a chunk more. Then you do everything you did in grade 10 in grade 11 for like a month, and then you add a ton more and lots of math. And then grade 12, they assume you know everything, they review nothing, and they just start brand new material. And you have to know all the previous material. BC believes in a repeating pattern up to then. Not other schools do, but we do, so you'll be fine. Okay, I think it's probably enough time. It was, where did I get the point to? Arnie. Which column you want?
I'll start with electron.
Which column?
Symbol.
Symbol. Okay, what's the symbol?
E.
E,
P.
P, N. Excellent. The only caveat, the E always has to have a minus sign on it because the mathematicians are jerks. Does anybody know why we have to have a minus sign on the E because mathematicians are jerks? Sorry? Everybody spoke at once, so you were the one responsible when you said something. What did you say?
When we combine them with, actually I'm not sure.
I mean, protons are positive. We don't have to write the positive. Yes? Yeah. There's a number in math that we represent like E, just like we represent pi with a particular symbol. And so there is a number that's made, and the mathematicians get irritated when they see E, and they think it's their E, and we're chemists are like, no, it's our E. So we put the charge just to distinguish it from the silly mathematicians. Okay, next person. Mari. Pick a column.
The charge electron.
Sure. Well, all the charges. Go.
Oh, all of them?
All of them.
I have two of them.
Oh, well, we'll be able to figure out the other one on the way.
So like a negative, and then a positive. No, yeah.
Never correct yourself. Just go. It's positive. Yeah.
Yeah.
Guess the last one.
Negative and positive.
Yes. Yeah. You say it again. The last,
Negative and positive.
which is
Neutral.
neutral. So that one's 0. Perfect. Nicely done. Also, keep in mind, if I'm asking people questions and they didn't put up their hand, that means they don't necessarily know the answer. So there's a couple rules to this. Number one, don't blurt out the answer when someone else is trying to work through it, because I use that as an opportunity to see if we can work through it and help develop an understanding. Obviously, if you're going to get called out of the blue, you might not know the answer. So you don't want people poking fun at that or treating that badly. So be supportive of everybody who's now in the position in the hot seat. We are not third year biomedical ethics, in which he taught entirely by sarcasm. Miyabi, pick one. Perfect. That works out quite well. Do you know what which ones are the heavy ones in terms of protons, electrons, and neutrons?
Electron is the not heavy.
Not heavy. Perfect. So we say that one is about 0. Do you know relative to each other, are the protons and neutrons the same or different? Same. So they're both 1 AMU. So they're both 1, and you may be wondering, like, what's AMU in terms of grams? This I am going to do on the board. If I take, I can't even start saying it, 6.
Just for the math.
If I take that many AMUs, I have 1 gram. So it's a very small amount of mass. But we've picked it very, very deliberately because 1 proton and 1 neutron are each 1 AMU, which means if you could just look at your periodic table, how many AMUs is oxygen?
Uh, 16.
16. I should have done the, sorry, I just realized, I called out again and I looked expectantly. I'm not used to using my app yet. Go back to that. Skill testing question. I'll ask someone else. If I have hydrogen, how many AMUs is that, please? AMUs of hydrogen, Jamie?
1.
1. Really skill testing question. If I have H2O, how many AMUs is that? Grayson?
18.
18. Oh, we're knocking it out of the park. So that's 8. It's still a really small number, but we know that. How does that help us? Well, if this whole thing is 18 AMUs, that means we know that if we take and I go out to the lab and I weigh out 18 grams of H2O, then I have 6. I'm gonna write. In grade 9, did you do scientific notation? Okay, so this number is too big to write, so I'm going to do it citation. 6.022 times 10 to the 23rd molecules of H2O. And I know that's pretty wild. If I measure it in grams, something I can do with a scale in the laboratory that you can do with your kitchen, I can now count the number of molecules. Not to 1 molecule, but you know, to the nearest maybe 100 million, depending on where you want to go in here, but to like 4 decimal places or 3 decimal places, that should be pretty good, depending on the quality of your scale. So now we can count atoms with mass, which is hugely useful, because it's really hard to get a small enough pair of tweezers to like count them individually. So if we can just weigh them out and then do a calculation and figure out how many molecules we have, that's going to be greatly interesting. That's Chem 11. But that is the whole point of why we learn this. Last one is Aiden.
I don't have them. I don't know.
Think of the Bohr model we just drew. Where were the electrons?
Electrons are in the inside, right? No, outside, and then
Outside.
the neutrons are in the inside.
Yeah, what was the inside called? It's the same as the center of a cell.
The nucleus.
The nucleus. Excellent. The word nucleus in Latin just means center, so biology and chemistry use it. It just means different things depending on what course you're in. So in biology and you're doing cell science, it'll be the same thing. And your electrons are on the outside, so we could call that the electron cloud, the electron shell, the electron level. What do you want to go with?
Cloud.
Cloud.
Yeah, electron cloud.
Electron cloud. Nicely done. We're we're going to skip that one for now. So we're going to ignore that for a second. I'm going to go straight to here. Pull out your periodic table, label what all those are. There's a couple things I have to go over about it.
That's not
Snowium.
That's not real.
A fake element named after Mr. Snow. This element does not exist. However, it does illustrate an important point that I always like going over when we start this. If you go on in chemistry and you discover a brand new element, there is a long-standing tradition in chemistry, going back hundreds and hundreds of years, that you name it after your grade 10 science teacher. So someday I hope to see a Nefeldium out there. And that goes for most things. If you ever discover something, you know, you're a young researcher, you find a new discovery, people are going to try and take advantage of you. You should probably bring it to me. And I'll take care of you. And make sure you get what you deserve. Don't worry about it. I'll help you out. Excellent. Fill in those things. I'm going to call on people to tell me what they represent in a moment.
Yeah.
Oh, and it's time.
It's time for lunch.
No, I have time medication too.
Oh.
Yeah.
My apologies.
If I don't take it, I turn purple and explode.
Is it from all the time travel, time lord?
It says not to take it with caffeine, so I don't have caffeine. I have coffee, so I fooled them. Ta-da!
I don't think that's how it works.
There was the gentleman who was told by his doctor, your liver is failing. You have to stop drinking alcohol. You cannot have one more glass. Do not drink alcohol ever again. Alcohol is really bad for your liver. There's a chemical process it has to do. You detoxify it. Drink too much, your liver can fail. So the doctor's like, no more alcohol ever. So he went home and he said, the doctor said I couldn't drink alcohol. But there's another orifice I could put it in. And he did. With the help of his spouse. He didn't die, but he came really close. They charged his wife with assault because she helped him. Because she should have known better, and that was so dumb.
Why would you?
It's called an enema. People used to do it for health reasons. Wine enemas in like Roman times were super common and really, really popular.
But also, people ate mummies in the Middle Ages.
Yeah, but people do weird enemas now. I had a mom whose children are not here and haven't been for a long time, had to double check my memory, who came in, and I'm doing an interview, and she's like, oh, you teach science, that's great. You should really incorporate more about urine therapy. And I'm like, what? And then she went on, and apparently her health company, she sells supplements and promotes urine therapy in which you drink it every day, as well as rub it on your skin.
Oh, that's
Yeah.
nice.
So I don't make fun of the Romans for doing weird things. We do weird things all over the world. And who knows? Maybe she's right. I don't think there's any evidence I've ever seen, but you know, it's a strange place, the world. Okay, Liam, you ready? What's the first one?
Okay, the first one is the atomic number.
Atomic number. Excellent. What does that represent?
That's like the amount of protons.
That's the amount of protons. So we call it the atomic number. Atomic number. And that's the number of protons. Oh, right. I had to check this the other year. I'm going to make sure. What is this?
Number.
Okay, good. Pound, old school, yeah. Something nowadays people seem to call it hashtag. That's a new name for it. Everybody knows that means the word number?
Yeah.
Okay. There's a few people who'd never, they just thought I was like making like a, you know, hashtag P. Post it somewhere. I don't know. Okay, next one. Let's go. Graham. Symbol. And why am I being so pedantic and going through all these? Because there's something I really need to tell you about symbol, because a lot of students come into here with a bad habit from English. And that is, what do you notice about all the symbols in the periodic table? Yes, your hand was first. I won't get out there.
The first letter is capitalized and the second letter, if there is one, isn't.
Right, and they have to be like that. So I've noticed some people have writing, they just learned this writing, where they capitalize everything, they like write in all caps. So the danger with that is that this is cobalt, a metal that you can exist with in the same room. I wouldn't eat it, but it's not that toxic. And this is carbon monoxide. This is the class we had the terrible stories.
Yes.
We'll try not to mention carbon monoxide ever again. However, if you write, for example, this is germanium, this, I don't know what that is, because that's a lowercase g that's just written really big. Is it supposed to be a capital, or are you just messy with your writing? You've got to have uppercase and lowercase. You know where uppercase and lowercase comes from, the words?
They were stored in separate cases in
Stored
the
in
printing press.
Printing press. And you wanted all the lowercase in the bottom because they use those the more often. And then when you had to grab a capital, you went up to the uppercase. Okay, next one. Well, those are the main ones I had to talk about. This is the name. Often with an EM at the end, except for aluminum. And if you say aluminium, that's okay. It's a variant, but it's not the official IUPAC name. And what's the last one called? Yeah, you can't call out. Neither of you can answer because both of you call. Yeah, because I'm training myself as much as I'm training you. So I'm going to go random. Matthew. Atomic mass. And what is the atomic mass? No, too many now. Okay.
It's like the weight of the atom.
It is, but it also isn't. It is very closely related to that. I will.
Oh wait.
No, I feel these three have done a lot.
Well, me.
But then other, yeah, but you just did one. I should give someone else an opportunity and torture you slightly.
Oh.
And then it literally came up with Bowen.
Yay!
What is it?
It's the AMUs. It's the protons and it's the average protons and neutrons.
Ooh, the key word there was average. So it's the average mass. No atom necessarily exists with that mass. It's an average in the same way. Did I do the family example last day with number of siblings? On average in Canada, if you are in a family, the number of children in that family, the number of siblings, is 2.3. Is there any family out there that has 2.3 children? No, because even if you cut off an arm and a leg, you're still a whole person. You can't have a third of a person. It doesn't make sense. You are a whole person or you're not a person. It's a binary either or. So that family either has 2, or it is 3, or it is 1. But it has to have a whole number worth of people. Same with the mass of a particular atom. It must have a whole number of protons and neutrons. But the average can have a decimal. Does anybody know what it's called when you have just the number? Not the atomic mass. It's another type of mass. Okay, we'll do it in a second. Okay. Open up the app again. Stop crashing. Come on, load. There we go. What is the charge if you're neutral? Rachel. There is no charge. In a neutral atom, what two subatomic particles have to equal each other? Yuma. Protons and electrons. Which one's negative? Electrons and protons. What kind of number is the atomic number, and what does it count? Noah. Pardon? Oh, it's terrible. What is the atomic number count? Look up. Number of protons. So if you want the number of protons of an atom, you just look at the atomic number. And if it's a counting number, what kind of number is that? Or to put it another way, what can't it be? Yeah, no, you're still up. Yeah. On the plate, batting away.
I was writing this down. I wasn't listening again.
Oh, that's okay. What type of number is the atomic number if it's a counting number? Or another way of putting it, what can't it be? No, he does that all the time. We ignore it. Oh. If you were counting, say, people, how many people can't you have?
0.
Oh, we could have, theoretically, we could have 0 people. Tell him, don't tell him.
Half a person.
Half a person, so no decimals. What kind of sets are called for math? What kind of numbers do we use when they can't have a decimal? Real numbers have decimals. Whole number will work. A whole number that counts the number of protons in an atom if all atoms of the same element have the same number, atomic number of protons. So the number we're looking for that is an exact mass for a particular element is called the mass number. The mass number is also a whole number. Oops. That counts the number of protons and neutrons in the nucleus. So, number of protons and number of neutrons. It's not located on your periodic table because it refers to an individual atom or collection of atoms. Yeah. Look over here. One second. Why did that do that? Don't do that. Here we go. Okay. Now, am I needing another minute to get anything done? Now I get to do the other thing that my app can do. Why are you waiting? Oh, the internet. There shouldn't be lag on the internet. What? Come on. Why is this taking so long? Is it even streaming now? It says it's streaming.
That's how Scuba works.
Is this going?
Everyone knows that.
Seems to think so. Oh, that's so annoying. Oh, that's at least good. Excellent. I have assigned you a partner. Grab that partner, find a spot on the board, grab a whiteboard pen, erase whatever's in front of you, and await further instructions. We will desegregate this classroom if it kills us. Grab your partner. Learn someone's name.
Baker.
Find your partner, find a spot at the whiteboard with the whiteboard pen.
Why is everyone eggs?
Jamie, do you have Arnie? Excellent. Rachel, do you have Matthew? Bo, do you have Rose? No? Excellent, there we go. Find a spot at the board. Layla, do you have Nick?
Can we erase this?
Yes, erase everything that's there. Layla, Nick?
Yeah.
Good. Liam and Marie.
Yes.
Mari,
Yes.
sorry.
Yeah.
Miyabi and Aiden.
No, I don't know.
Miyabi? There, Aiden. Excellent. Noah and Yuma. Where's Yuma? There you go. And Graham. And where's Grayson?
Not here.
But I put in attendance. Okay.
No, he's in the bathroom.
Oh. Find a spot. We'll send him to you when he comes back.
It's obvious.
I thought maybe he like snuck away and I didn't notice, and he's just out like living his best life, not doing chemistry. Okay. What I would like you to do is I would like you to answer that question, but I want you to draw the Bohr model of atom X and atom Y with the correct number of protons, neutrons, and electrons. They're the atoms. So we have atom X and atom Y. Using that information, draw the Bohr model of both. You can grab a periodic table if you need to.
Wait, I got this.
There's a box of pens on my desk right there. You can grab that. Yeah, those. Just grab one. And then below them, write all the ways they're the same and all the ways that they're different. And then once you're done, you can have a seat.
They're the same in all. My apologies.
Mass number is.
That's not too early.
You're with Graham. Graham over here. Right here. Graham Tuber. It appears none of the kitchen jobs are done, and nobody returned the prep snack boxes this morning. Write a little sentence below about their differences and their similarities, and then have a seat once you've done so.
Oh wait.
How detailed must we be?
As long as you feel you're a thorough.
Yeah.
That makes it the same. Wait, hold on. We're not thorough. Oh, they're
But
the
it's
same.
all
What happened?
information.
Please grab those boys this afternoon.
What? Oh, okay, so I was like, oh, were you saying the coal
Gotta
mine?
make sure all jobs are inspected at night after cycle.
What isn't covered in this?
Once you've written your sentence and you're good, you can have a seat. You're good to go.
It's so far.
I will be getting hopefully more whitebirds because this is crowded, I know.
Some off-road.
Nope.
This did feel awfully suspicious.
No way you give us two identical.
I disagree. This every way to give us two identical atoms.
Okay. When you're done with the pens, please remember to put the cap back on, otherwise they dry out. Let's go through, take a look. Number one, this group. Oh, perfect. 100%. 120 out of 120. Fantastic. I look at it, I see the number of protons, a nice simple electron structure. If I'm marking at home, I'm sitting down, I've got a nice festive pen, green or purple or something. Nice music's playing, got my coffee, going through the papers. Get this, beautiful. Then I go to here, or really any one of these, and I go, oh my God, I have to count. They drew rings and put dots. They didn't use the efficient method. Now I've got to go like 2, 4, 2, 2, 4, 6. It's terrible. Now, is it right? Of course it's right. Of course it's right. But at that point, I just shut off the music. I put away my festive pen. I get out the angry red pen. I put away my coffee. I might put rocks in my shoes. And then I look at it more closely. And I go, yeah, that's basically right. But look at this. There's a gap there, minus a half. Oh, look at that one. Also a gap, minus a half. Adam, why? Is that an M or a W? What is an atto? I don't know. I can't read that. No. But you did okay. You got like 4 out of 5. Oh, look, I found something else. I don't even know what it is. I just don't like it. It's 3.5. Yeah. Oh, look. They wrote in all caps, which is fine for here, but I just don't like it. 2 out of 5. However, you are right. ANUs. It has the same amount of protons and neutrons. Could be different number of electrons. Oh, didn't include the period. Punctuation. And, use the word number. No abbreviations. But just to drive the point home, I'm going to abbreviate abbreviations.
That's great.
This person used X's and they spaced them out. They didn't even pair them together. Do we have to do that in grade 10? Do we have to pair them? No. But you know what? It would have been better if you did, and that would have been extending. So this one's developing high. Yeah. But it's right. Maybe it's proficient low. You know, the one where the teacher can say, you're good enough, but you shouldn't feel like it. Go to this one. Oh. Extending high. Maybe with a heart. No, that would be inappropriate. A smiley face. And a good job. I was rooting for you all along. Oh. I have to count again. And I'm lazy. Is that really an 8?
Yeah.
I think it's sideways. That's actually a 9. So I'm going to write 8 neutrons,
No, that's an 8.
not 9.
It's infinite.
No.
Yeah, but you're not here to yell while I'm marking. Oh, look! It's drawn efficiently. Fantastic. Extending high. A new one I've done with a plus. Fantastic. I kid, of course. All of these are right. Everybody, there's only one I've seen that was wrong in a previous class. So you're all fantastic. It's good. But the reason I like these is because for this particular purpose, even go with the model that's the most efficient, makes it easier to mark, and I can get through it, and I can see that you're right. The practical difference is if you make more complicated models when you don't need to, you are more likely to make a mistake. And I have to slow down to mark it. And every time the teacher slows down, they start to notice mistakes. Okay, excellent. That brings us to isotopes.
Yay, I love isotopes.
I ate one. Well, we all eat them because everything's an isotope. But I ate an unusual one.
How is it unusual?
I'm going to go through it. Oh, right. Oh, sorry. I forgot to go over this. There's a page on here of everything we've just done. So if you weren't here for grade 9, this is basically all the Bohr model stuff that you should know from grade 9. It's summarized on this particular page. We've done notes on it. We only really go up to 288, and technically 2, because we go up to calcium, element 20. But You should know it goes all the way up to 18. You should be okay to do that if you needed to, but you don't tend to get examples like that on tests or quizzes. We already drew our atom. So, isotopes. Isotope has the same number of protons, but it has a different number of neutrons. So it has a different, you change the number of neutrons.
You changed the game. Not really. It's practically the same thing.
Same number of protons equals an isotope of the same element. You have normal hydrogen. How many neutrons does hydrogen? Oh, I haven't shown you this. When we put numbers above like that, that's the mass number. So that number there is the protons plus the number of neutrons. If we were to write the number of protons, you actually put it here, and you put the charge there. We'll get used to that. For hydrogen 1, which is like the most 99.9999% of the hydrogen you find, how many neutrons does that have?
0.
Where'd my, oh. How many neutrons does that have? No, press, and then I gotta use the app. People have to have points. Layla? 0, excellent. So no neutrons. How many neutrons does hydrogen 2 have? Rose? I already gave her the point.
You take away the point.
I'm going to take away the point. I don't know how. Oh, I can give her negative points. Huh. Nick? 1. How many neutrons in that one? 2. They just have special names because hydrogen is fairly important to us in terms of chemistry. That's known as deuterium. So you ever see that, they just mean heavy hydrogen, and that's called tritium. And if you were, say, shielding a nuclear reactor, a really easy way to have flexible shielding is that you would just make water, but you'd make the water with deuterium. When you make the water with deuterium, you have what's called heavy water. And the hydrogen works the same as regular hydrogen. It just works as regular water. You can move it through your system, but you can cover the radioactive material. And because it's a little bit more dense, it'll block more of the radiation. You just fill up the water until everything is stopped.
Why don't they use tritium?
It's much more rare, difficult to get a hold of. I had a drop of deuterium water, heavy water, pure, in a lab, and the professor was like, hey, want to taste this? So he put a drop in my tongue, and I tasted it. It tastes just like water. Because instead of being 18, its weight is 20. Almost no difference. If you were able to drink liters and liters of it and replace all the water in your body with heavy water, you would probably run into trouble, because although it reacts exactly the same, it is heavier, and you're made of a lot of water, so all your reactions would start going a little bit slower. And it would just be like, you know, there was a brake on the engine of a car or something. It would just everything would be a little bit worse. But it's naturally present. There's a whole World War II story about that.
What? I don't want to know. I don't want to know.
I want to know.
It's kind of cool. Okay, World War II. Keep in mind, geography is not my strong point. So here's like Norway and what? Sweden? What's next to Norway?
Sweden, Denmark.
Keep in mind, when I say geography is not my strong point, I mean really not. I thought Korea was next to Norway for a long time. Like I was an adult before I learned differently, because I thought that's just where all the peninsulas were in the world.
We live in
I thought my teacher said that. I was wrong. And then there's like Europe and like other things. Africa, I guess. There's like a whole sea here. Russia. Anyway. So, the Nazis, World War II, and the Allies and the Axis, but specifically Germany and the Nazis, they're both trying to develop atomic weapons. And deuterium is a key part of the research of developing atomic weapons. They're using it for shielding. They're using it for all sorts of stuff. It's an incredibly rare form of hydrogen. It's like parts per billion in seawater. So you need access to a lot of seawater to separate it out. And you need somewhere with a lot of power. And so when they were looking for where is that going to be, we have the research going on in Los Alamos for the Allies. And they were trying to figure out where was Germany doing its research. Well, they had taken over Norway, and there was a big ocean here, I don't know what that says. And then there's a river, and then there's a hydroelectric dam. And they did random samples. So when their submarines went out all over the world, they would collect samples, and they found in here there was heavy water on average more often than anywhere else in the world. So it was being released from the lab. So they knew the lab had to be somewhere near here. They knew they needed a lot of power. There's a hydroelectric dam that they could have taken over. And they also noticed, you take over a country, but communication doesn't stop. The communication from the towns around here had completely stopped. No communication in and out. So they're like, I'll bet you it's at that dam. So the Allies came up with a plan, we're going to blow up the dam. So they get a bunch of, commandos, and they, in this case, the airborne, and they fly over top, and they drop them in. There's a little town right here that they're going to drop near, get resources and supplies, blow up the dam. And they landed here. Wrong side. So what did they do?
They blew up the wrong dam.
No, they crawled in a cave and died. So that's the bad part of the story. Because, number one, blow up the dam. If you can't blow up the dam, number two, don't get caught. We don't want them to know we're coming. So they can't go to a town and notify anybody. There's towns here, but they can't tell them that they're there, so they just hid until they died. So now comes in team number two. Team number two manages to drop in here. They go into the town, figure out where the dam is, go into the dam, blow up the dam. It probably delayed their efforts by about 3 to 6 months, and that is the reason why the Allies developed the atomic weapons first and not Germany. One of the reasons. There's another reason is that in the Allies, the person in charge was more of an engineer, and engineers know that if you're trying to build something efficiently, you build it in spheres. That concentrates all the matter. But the person who was developing it in Germany was doing everything with squares and cubes. Why?
Physics.
And actually, no, it's a preference. You can do both. It made his calculations easier. Because squares, you can calculate area and volume way easier than spheres.
That's what I meant.
Yeah. Well, you do the math. And so that actually slowed them down because it wasn't the best system. So there's a couple of reasons for that. So, and all of that was based on just where they were tracking deuterium in the world. World War II story. Yeah. With a sad element. Do I know any happy stories? Anyway, the number at the end of a word, all of these are the mass number. So if I say hydrogen 1, hydrogen 2, hydrogen 3, that 1, 2, 3 is referring to the mass number. If I give you something like argon 43, that is the mass number. And the mass number is the number of protons plus the number of neutrons. We have uranium 238 and uranium 235. Does anybody know which is the dangerous one? 235. 235 is the radioactive one. Chemically, they're identical. This is rarer, but it is when you mine uranium ore. That's the one that's making it radioactive. This is stable. It's really heavy. It's heavier than lead. In fact, in the processing of uranium, the U.S. has a lot of processed uranium that is all this because they've taken all the radioactive stuff out. So they used it for keels on sailboats for the World Cup because you could make a very narrow keel with the least amount of friction, but was heavy enough to hold the sailboat down. This one is the radioactive one. Canada has tons of it. We're one of the major exports of uranium throughout the world. We've got all sorts of stuff up there. Well, we sell nuclear reactors, the CANDU reactor. That's considered the safest reactor in the entire world. If it breaks down, it automatically, the way it falls apart shuts down the reactor so that you can't get things where they accidentally blow up. The reactors that blew up at both in Chernobyl were built in a way that if the electricity turned off, they would blow up. And yes.
So uranium-238 is like as safe as like, well,
It's as safe as lead.
okay.
It might be poisonous to eat, but it's not radioactive.
Okay.
It's a metal. Lots of metals aren't stuff you should necessarily eat. Even iron, which we use in our blood, you shouldn't like eat a lot of it. But you need some of it. Does anybody know how you get your iron for the day? Pardon? It's in spinach. You can literally cook in an iron pan, and tiny bits of iron that get in your food will feed you iron. There's a demo I do in Chem 12. I take cereal and I crush it. And I put lots of water and I mush it up. And I stick in a bar magnet and I pull it out. And there's little shards of pure iron on it. It's just metal. And they add it to the cereal and they say it's iron fortified. Well, yeah, you can absorb small amounts of iron. Literally, if you lick iron, you will absorb iron. You can buy little metal fish. A Canadian doctor, healthcare professional, invented, there was an area of the world that they were in, and they noticed the number one deficiency was iron deficiency. And they came up with the idea that, like, if we just added little iron bits to their food, it would just come off into the food. They get their iron, and you take the bit out and just reuse it next time. It would last, like, for a really long time. So they made it in orchid flour, and nobody used it because that was yucky. So then they made it into a little fish, and then everybody used it because they said it was lucky. And then they got more iron. You can buy it right now. If you buy one in a country like Canada or something, they'll use the money to go send it to places where they are really iron deficient. So literally, you should eat iron.
No.
Yeah, but not like huge amounts of it. Don't break your teeth. So, I want you to calculate the number of neutrons in each one. Oh, what's this number? Look at your periodic table at the numbers you know about uranium. What's that number? I'm going to ask. Rose. Where's Rose? Oh, I'm asking you what that number is, but first find uranium on the periodic table.
Oh, there it is. Lovely.
It's in a weird spot. Look, think.
Aluminum number 92.
Don't like what I said about calling it up. It's in the purple area.
Oh, I see it.
Okay? So what is that number? That's the atomic number. And what subatomic particle does that count? The atomic number. Protons, neutrons, or electrons? What the atomic number is the same as the number of protons, neutrons, protons. There. So that's the number of protons. If you want to write the number of protons for the element, you put it down here. That is the mass number. Calculate for me the number of neutrons. Mari? Oh, I'll give you a minute.
What's the question?
Number of neutrons in uranium-238. And you're allowed to use your calculator if you want. I still use my fingers during tests.
I also use my fingers.
It's so reliable. They're always there.
I sometimes.
Well, at least I'm privileged for them always there. I guess they could cut them off.
I use the. I sometimes when I need to count to 60. I use.
Clever.
I was wondering, how does the element define like to be radioactive? Like the number of
146.
neutrons?
What'd you say?
146.
146?
Yeah.
Okay. What defines it as radioactivity is that it gives off radiation. So there's lots of isotopes that aren't radioactive. So the types of radiation is alpha. There's alpha radiation, where it literally spits out a piece of helium. So it gets lighter. You take 4 off of there and 2 off of there. So if it spat out a piece of helium, it would become 234 and 90, whatever that element is. I can't remember. There's also radiation where it spits out a really fast electron. So it's moving at high speed. That's known as beta radiation. That's alpha radiation. And then there's,
Thorium.
no, that's a photon, a high energy photon of gamma radiation. And that's the third type of radiation. So if an element is giving off any of those, it's radioactive. You cannot predict it just by looking at the numbers. So it's an experimental determination.
How does the number of neutrons make that happen?
Neutrons, they're not positive, they're not negative, but they kind of act as glue for the nucleus. So if you have too little, there's not enough force holding it together, and it may start spitting stuff off. And then when it gets stable, it'll stop. But also, if it has too many, it's like, ever build a model and you use way too much glue and it doesn't hold together very well? Kind of like that. You've got way too many neutrons, it'll start spitting stuff off until it's at a stable thing. Right now, if you look at the periodic table,
So is uranium with atomic mass 238 the most stable one?
yeah, that's the stable one.
And the most abundant. There's also
The most abundant and most stable, because all the unstable ones eventually go away. So,
You need new ones.
yeah, this one goes through a variety, like this one becomes something radioactive, it becomes something radioactive and steps down, and eventually ends up at stable lead. So that means when you get a piece of rock, and it's like 10% uranium and 90% lead, well, you know it originally started as all radioactive uranium, and slowly it converts at what's called a half-life, and you can then calculate how old that rock is. So that's how they do dating with rocks. If you do it with carbon, which is incorporated in living things, that's carbon dating. The half-life of uranium is a really long time, so you can use that to date things like the Earth. The carbon dating has a half-life around 2,000 years, so that's useful for dating like plants and animals and things that have died where the carbon is now set. And it's carbon-14 is the radioactive one. But if it goes too long, you're dealing with millions of years, it's all turned into the other stuff. You can't date it anymore. But that's how they date things as well. They look at the products.
So the nuclear reactions and the bombs and stuff, they were
Oh, yeah. So,
forcibly separated.
well, I think the uranium, this particular radiation, those are the main ones you learn about in your next, not this year. Actually, you learn it in Physics 11. But there's also a type of radiation where it gives off a high-speed neutron. So let's say this gives off 3 neutrons. Boom, boom, boom. The atom is so unstable of the uranium that if one neutron hits it, it gives off 3 more. And then each one of those will hit another uranium, and then you have now 9, and then it keeps multiplying like that. That's a chain reaction, and that's what actually blows up the bomb. But if it doesn't hit a uranium, but it just flies off into the air, it hits nothing, then the chain reaction stops. So what you need to do to make a bomb, a nuclear bomb, is just have enough. So that's known as critical mass. So if you have a critical mass of uranium, so all you have to do is have less than critical mass in one hand, less than critical mass in the other hand, and put them together fast, and then you'll have a critical mass, and all the neutrons will start hitting, they'll all blow up at once, because you get a cascading effect. They don't do this anymore, but for a number of summers, the Atomic Institute would hire grade 11 students. So students who haven't graduated, and they would deliberately hire C plus B. They didn't look for the top students in the class, and they would say, we want you to use the public library, the internet, Google, and we want you to design a working nuclear weapon. And grade 11 students would go and research, and they'd come up and give them their plans, and in most cases they'd be like, yep, that would work. Because it's really easy. All you have to do is get the uranium, put it together, and go boom. If you're not worried about the person surviving that process, it's even easier, because then you don't even have to do it at a distance. So it's really easy to make a nuclear weapon. The hard part is that this part is rare. If these are chemically identical, How will you get pure uranium-235? How would you separate them?
Mass, centrifugal force.
Centrifugal force. So you do it by mass, because that one's heavier. And you know, like when you pan for gold, the heavy stuff ends up at the bottom? A centrifuge just spins it, and it's like a really advanced form of panning. So you pan, basically. But also it's a solid. So you have a big chunk of, like it's not going to pan, and it'll atom. So first you have to make it a gas. So you have to vaporize the uranium. Then you have to spin it really fast. And then all the heavy ones that come out, you take off, and eventually you purify it down to uranium-235. That's the hard part. There was a virus, I don't think it was the Stuxnet virus, that came out in the early 2000s, late 90s, and people didn't know what this virus did. And they were like, it's infecting all of our computers, but it's not doing anything. What they realized it was doing is if it got into a centrifuge, it would mess the centrifuge up so it wouldn't quite work properly. And they think it was released by a government to prevent other governments from being able to develop nuclear weapons. So it was actually made like, you know, one of like CIA, CSIS, you know, those types of agencies to target other countries that were trying to develop nuclear capability. Because this is really hard. You need a lot of really complex technology to do that. And if you can get it into their computer, it would slow them down. Does anybody know who CSIS is?
Is the Canadian equivalent of the FBI?
No.
Of the
CIA.
Sorry.
They're better than the CIA. How many of you have heard of the CIA? How many of you before this moment had heard of CSIS? Much fewer. Therefore, better. More secret. Huh? Okay, last one. What is the number of neutrons in uranium-235? Noah. Oh, what's this number?
235.
And how do you calculate it? What does it represent? Mass number. And mass number is what plus what? Protons and neutrons. And that represents the number of atomic number. So it's the number of protons. Protons. So if that's the protons plus neutrons, that's the protons. What would you do to just get the number of neutrons? Yeah, go ahead, minus it. Got a calculator. Oh. You can do it quickly on your phone. And then afterwards, put your phone away. Now see, with my app, I can notice I have not asked, I said I have not asked Violet a question. But Violet's also not here. That would explain that.
Interesting.
143. Which makes sense. 238, 235, it's 3 less. That was 146 neutrons. This is 143 neutrons. Good? Any questions? Okay, I'm going to pop all the way back here. I would like you to draw the Bohr model of boron. Label the electron shells or electron energy levels, the outermost shell, the valence electrons, the inner electrons, the inner energy levels, and the nucleus. I recommend you do not draw it to scale. I can tell you why in a moment. However, new groups.
Mr. Neufeld,
Yo, what up, my homie G?
this isn't to scale.
Pardon?
This isn't to scale.
It should not be to scale. Scale would be bad.
Mr. Neufeld,
Yo.
you can't see anything. It's to scale.
No, to scale means you draw it so you can see it, but you make sure everything's proportional.
Yeah, no.
Okay, grab your person. Do it on the board. Erase what's there, grab your person. Go.
Why is everyone else in Why is everyone eggs, Mr. Neufeld?
Everyone is an egg because you haven't hatched yet. For some reason, you've hatched. So is Graham. That's weird.
Oh, me.
Yeah, you haven't hatched. I don't know.
Egg. Haha.
Oh, I know why you two have hatched. You're in Privet House. Last year, no, I'm the only first teacher that uses this. So last year I put every person in the house into a class dojo class just to quickly do attendance for certain things. And so you have existed. Oh my God. Are you okay?
I'm good. I just don't think the box is good.
No, you're allowed to do that. That's fine. The boxes are heavy. Do whatever you like.
Hey, I'm joking. Be nice like yourself.
Okay, I'm gonna put it down. Oh my God. Stop! I just realized what time it was. And it's good. The bell's gonna go in like 30 seconds, so I get everybody's eyes and ears. A heads up, next week you will have a quiz on what we've done in the Bohr model and what we're going to do on, what's today? Friday?
What are we gonna do? What day?
I'll post it on the Google Class.
Can you post it? Not at 12 o'clock, please.
You just see it the next morning. I wouldn't post it at 12 o'clock the day before. That'd be insane.
Yeah.
Yeah. No, so our Bohr model, a little bit next week.
I'd post it the night before.
Okay? You posted the night before?
Yes.
No. Poor, who was it? Ryan, who was on duty one morning. Peter had posted the schedule at 12:30 a.m. He was on duty at 7 a.m. and I would have gone to bed.
Remember when Finley would always say, sorry for the email every Omni email?
Yes. Poor
The good old days.
guy. Oh,